Okay, this is part 3. So this is going to cover 16 through 21. So a lot of our stoichiometry, empirical and molecular formulas, and just interpreting your problems and pulling the right stuff out of there. So for number 16, what we've got in front of us is we have a table. And so it says using stoichiometry, but really what you're going to be doing is you're just going to be doing conversions. It's not really stoichiometry because, as you can see, I tell you right here, there's not going to be any mole bridges or mole ratios, and that's really what stoichiometry is all about. But we will be doing conversions, so this is all about conversions. Okay, so their first little one that we've got right here. Hopefully you are practicing your naming. This is sulfuric acid, and they go ahead and give us the molar mass. Just a reminder, so molar mass we're going to be getting from, use your periodic table and add up masses, okay? So when we look at that first column, we're going to be looking for molar masses, all right? Then we're going to be looking for, or we'll have other ways such as unknown. We're going to have to do it another way. When we have mass of sample is usually what's given to you. Moles of sample, that's directly related to that mass of sample. So it's just a new kind of measurement. So that right here, this is just a conversion using usually that molar mass, okay? And then finally, number of atoms, this is where we're going to use Avogadro's number. I will be writing with the E, so 6.02 E23. However, on the first day of school, I'm going to remind you of this. When it comes down to the AP exam, we cannot use that E. I'm going to use it just for timing purposes in this video, and I just want you to get the process down. We'll perfect those little minor skills later. Okay, so let's look at our first thing. We've got sulfuric acid. They went ahead and gave us our molar mass as well as a mass of the sample. Okay, so we're going to do this first one in, there we go. Needed a color you guys could see. All right, so we're going to have sulfuric acid. We're going to start with that mass of samples. So you always start with what's given to you. Molar mass is usually not where you start, ever, okay? That's a tool that we use to make our conversion. So we're going to start with what we're given, okay? 0.825. And this is grams of, I'm going to go ahead and put sulfuric acid, all right? So this is SA. All right, sulfuric acid. I'm going to make my railroad tracks. I'm going to bring my words down and to the right. So especially if you had me as a teacher, that is something that I really try drilling into your head. Anytime you're doing these conversions, you're using railroad tracks, words come down to the right because words divided by words is equal to 1, and that's what we want. We want to cancel things out, such as these grams, okay? So we're going to have grams of sulfuric acid over here, and we know that we want to convert into moles of sulfuric acid. So we're going to start with that, and we know that 1 mole of sulfuric acid is its molar mass. So when we plug this in, we're going to end up with 0.00840 moles. Notice, none of these zeros counted, so I went ahead and took it to 3 sig figs because that's what we have on both of these numbers, okay? All right, and then we are going to, so that's going to be our moles of sample, so we can say 0.00840 moles, okay? Number of atoms, we're going to take that moles, and we are going to bring words down and to the right, so we have moles of sulfuric acid. And we know that 1 mole of sulfuric acid is equal to, when we're looking for atoms or molecules or whatever, it's going to be 6.02 times 10 to the 23rd atoms, or whatever we want to say, okay? So once again, now we're going to multiply, and you're going to get 5.06, okay, I'm going to keep the 3 sig figs, times 10 to the 21 atoms. And I actually should not say atoms. This should actually be molecules. There we go. Okay, so filling it out in our table, 5.06 times 10 to the 21 molecules. Make sure you are showing all of your work. I know I don't give you a lot of space there, so pull out a piece of paper, and I would do it on a piece of paper so that you don't forget how to do these easy conversions. Okay, I'm going to scrunchel this up so I have some more room. Okay, so our next one, we have some chromium 3 oxide. Okay, and so for that, we are going to look at what information is given to us. And they're starting us over here. So we are starting at number of atoms. So I'm going to start with what is given to me. Okay, so we'll just call this chromium. Yeah, we'll just write out the formula. It's okay. It won't take that much room. All right, so 9.63. I'm going to say E23. And this is molecules. Make sure you're writing that extra C on there so you don't confuse it with the mole, okay, of Cr2O3. All right. Now I'm going to set up the rest of my railroad tracks and bring words down to the right. And I have molecules of Cr2O3. Okay. And I want to get it into moles. You can't just go from a chemistry word. I used to call them funky chemistry words, okay? And you can't go straight from that into mass. There's no conversion there. So you have to go through the mole. And so we know that 1 mole is obviously 6.02 times 10 to the 23rd molecules, okay? So when we type this into our calculator, remember you're going to be multiplying across and dividing down, okay? Multiply across, push equals, divide down. Here, obviously, we have something multiplied by 1, so you don't have to really include that. So when you do that, you get the answer. Let me type it in. Okay, just typed it in. You get 1.599667. So going to 3 sig figs, I'm going to go ahead and say it's 1.5. Nope. 1. Since we have that 599, I need to get to this part, so I'm going to use that to round. So everything basically bumps up. And I have 1.60 moles. Okay. So we have this 1.60 moles. So I'm going to write that in here. And now we're going to use that 1.60 moles to figure out the mass of our sample, right? So we first need to look at our periodic table. We need to get our little molar mass of chromium 3 oxide. So each chromium is 51.996 grams, and each oxygen is 15.99. I'm okay with you rounding up for this purpose today. So 52, and we have 16. So the molar mass is going to be 52 times 2 plus 16 times 3. I wrote 2 different notations there. That's okay. 52 times 2 plus 16 times 3. So I get about 152 grams per mole. Okay, that's very rounded. Okay, so 152. So I'm going to use now this 1.60 moles, and I'm going to continue it on. And I'm going to say moles of chromium 3 oxide. Okay. Okay, so we know that 1 mole of this is going to be about 152 grams. So now it's just straight multiplication. Don't have to worry about that 1. So we're going to multiply it by 1.60. And I'm going to leave it for 3 significant figures again. So I'm going to say 243 grams. Okay, so you have a sample of 243. Okay? All right. The next one, they're giving you a mass of sample and moles of sample. So this is kind of tough, but what you need to use on this one is that what the definition of molar mass is. So we said use the periodic table, add up masses, but it's also, look at the word itself, okay? It is also grams per mole. So if you notice, we're giving you a mass of a sample in grams, and we're giving you moles of a sample. I'm sorry, per 1 mole. So you're going to take the grams, and then you're going to apply the moles that are also there. All right, so if we have 56.8 grams, I'm going to divide it by the 0.476 moles, and you should be able to get your gram per mole. And that right there is molar mass. It's a sneaky way to make you apply just what the words are telling you. And it happens a lot in your AP questions. They're really easy questions, but they're easily missed if you don't know what your definitions are. All right, so our molar mass for that, I took 56.8 divided by 0.476, and I've got, let's do 3 sig figs, so 119 is going to be my molar mass. You don't need to go look it up. If you want to, you can, but you don't have to. All right, so this is 119. All right, so now we can move across. You didn't really need the molar mass to do this last part, so we could have started back where we have 0.476 moles. Make our railroad track, bring moles down. We know 1 mole of this is 6.02 times 10 to the 23rd, right? Excuse me. And so if we multiply those two together, we get 2.86. If you want to round it up to 7, that's fine. I'll tell you why I leave it at 6, probably on the first day of school when we start talking about rounding again. But times 10 to the 23rd. So if you said 87, that's okay too. And this is formula units because we don't know what we're dealing with. Okay. All right. And then the last one, I think I can leave to you. Make sure you use your formula chart, your periodic table, and you look up this guy right here. And you're going to get your molar mass, and then you can apply that to get this. Just know, so you're going from moles, you're going to do something that looks very similar to this, and then you'll do a mole to mass conversion, where you have 1 mole is equal to mass, the molar mass that you find for Mo. Okay, so check on your periodic table. I think it's atomic number 42. Okay. All right, so that's your basics into your conversions again. So hopefully that felt a little comfortable after you started running through it. Okay, so that leads us into number 17, which is covering isotopes. So just a quick reminder, your isotopes are same atomic number, which in a previous video, I told you is your number of protons, right? We don't mess with your number of protons, but different number of neutrons. So when we are dealing with an isotope, we are dealing with the change in that mass number, okay? And so when you name your different isotopes, as you can see, these guys are all neon. We would call this neon 20, neon 21, neon 22. You're defining it by its mass number, okay? It's telling you your different number of neutrons. All that does is tells you which one is the little skinny neon, which one's the fat neon. And that's the way I like to think of it, is it's not really pertinent to how it interacts with others besides that difference in mass. But it's so small that even that doesn't really affect it too much. So we're just dealing with a different mass number. It's just how many neutrons are naturally found in there. So we do know that when we are looking at our periodic table, all those decimals are coming from the idea that these are weighted averages, right? So meaning just like when you guys are in class, right? And your teacher tells you, okay, so your exams are worth 40%, your daily work is only worth 20%, and then your, I guess for science, your labs are 40%, right? You know that if you do all your daily work, but you bomb every single test, there's going to be something wrong with your grade. And that's because these are weighted differently, right? So same thing with isotopes. If you have different abundances, okay, they're going to affect that molar mass that we get to see on the periodic table. So when you are asked to find your average atomic mass, I put the steps together for you in your problem. I say percent to decimal, multiply the mass, add together. And it's really just that simple. So you're looking at the relative masses that they're providing to you, okay, and your percent abundance. So here we've got 19.992 units, okay, and there's a 90.92%. And so you can look at your periodic table right now. Look up neon's mass right now. It is 20.180, technically, all right? And that kind of gets pulled towards the 20 because of this 19.992. It's 90%. That's how often you'll find that in nature. These other ones are so small, but they do pull it up a little bit higher than 19.99. That's where it comes from. So how to do this? So we're going to basically take your mass and we are going to multiply it by if these were decimals. So that means you take that decimal and go 2 to the left. So what you're doing is you're dividing it by 100, okay? So you're taking 90 out of 100, right? So we're going to say 0.9092. And if I multiply those together, I'm going to get 18.1. Let's see what we should be doing. I have 5 sig figs here. I have 4 here. We're going to go to 4 sig figs. So 1/8. We're going to round up to 1/8. Okay? We're going to leave that alone. That's neon 20. Okay? Neon 21, we're going to have our mass, which is 20.994 units. We're going to multiply it by this guy changed into a decimal. So 0.0257. Now this one I have 3 significant figures that we're going to round to. So let's go ahead and type that in. And you get 0.53. I'm going to leave mine at 9. Again, there's a special rule that I always follow when I'm dealing with my 5s. If you round it up to 540, it's okay. And then finally our last one, we've got 21.991. And we're going to multiply that by 0.0882. So when we type that in, we get 1.94, okay? So now what you do is now we're gonna add them all together. And so what you just did was you took how much did each one apply to your total average? Just like you have 40% tests, 40% labs, 20% daily grade, each one gets added together to give you a total average at your every 6 weeks, right? So when we add these together, we get 18.18 plus 0.539 plus 1.94, and I get 20.6. We have to follow this, right? So 2 decimal places because we're adding them together. So 2 decimal places, 20.66 grams per mole. And that's how you do isotopes, okay? It will not always be in this pretty little table that we provided. So sometimes you're gonna have to read the words and organize it into your own table. Okay, so number 18 is talking about percent composition. So when we do percent composition, the big idea is that you're going to be doing part over whole, you're gonna multiply it by 100. Okay, so you're gonna look at each individual molar mass, multiply it by its little subscript, and then you're gonna put it over the total mass here and multiply it by 100 to make it that percent, okay? So first thing we're gonna do is let's look up all of our different things on the periodic table. So nickel has a molar mass, okay, of, I just had it, 58.693 grams per mole, okay? Phosphorus has one of 30.974 grams per mole. Oxygen has the 15.999. And that's it. All right, cool. So now what we're going to do is let's figure out what each one has. So there's 3 nickels. So we're going to multiply this guy by 3. And I'm just going to put everything to 2 decimal places. All right, just for ease sake. All right, so we're going to multiply this 58.693 times 3, and we get 176.08 grams. Phosphorus, there are 2. So we're going to multiply this guy by 2, and we get 61.95 grams. And then finally, oxygen, we have 4 inside the parentheses. We're going to apply the 2 to it, so we're going to multiply it by 8. We multiply it by 8, we get 127.99 grams. Okay, so let's get our total mass. So if we add these all up and I stick with 2 decimal places, we're going to go 366.02 grams total. Okay, so now what we're going to do is this little part up here, right? So we're going to say 176.08. We're going to divide it by our total, which is 366.02. We're going to push equals, and then we're going to multiply by 100. Okay? So you should be getting, for nickel, 48.11%. Okay? I'm going to go ahead and let you do the rest of these. I don't think they're too bad. If you're having trouble, just let me know. But a good way to check yourself is make sure they come out to be about 100%. Okay. Okay, so now we're on number 19, which is talking about empirical and molecular formulas. So just a quick reminder, I guess I'll write it up here. When you have your empirical formula, remember that is your simplest formula, okay? So what that means is that if you had something like C2O4, right? This would not be considered the empirical formula. What would be considered the empirical formula is reducing these 2 numbers down. They both have a common factor of 2, so we could say CO2 would be the empirical formula. This would be considered a molecular formula, or the true formula, okay? Now, when we go to figure out our empirical formula, what you always do is they usually give you percents, right? And the percents are actually, those are probably the easiest ones to deal with. So when you have a percent, you're going to do percent is going to change right into grams. And the reason why is because you're going to assume a 100 gram sample. So if you assume a 100 gram sample, you now can say whatever the percentage is the amount you have, right? And that kind of makes it easy. So once you have things in grams, you're going to go from grams to moles, okay? And then you're going to divide by the smallest, and those should be your subscripts. If you get to one where you have like a 0.5 or a 0.25, you're going to have to multiply all of your subscripts by whatever number will get it to a whole number. So key idea here is you do want whole numbers, or things that are so close to whole numbers that they can be rounded and you're not really destroying what's happening here. When we get to it, your molecular formula is going to be, you're going to take masses, right? So you're going to put the big number on top. So you're going to say molecular formula mass, or your true formula mass. So in here you can see that it has a molecular weight of that. That's your molecular formula mass. You're going to divide it by your empirical formula mass. So, oh my gosh. There we go. So you're going to divide it by your empirical formula mass, which you just get from putting, using your periodic table. And then you are going to get a ratio, and that ratio is what you multiply by all of your subscripts. Okay, so we are going to go ahead and start dealing with this question. I'll push that up to the side. We're going to make you just a little bit smaller so we can see our work. All right, so what we've got is we have determined the empirical formula for a compound which has 26.6%, 35.4%, and 38.1%. So we're going to change all of those to grams, okay? And I'm going to say for potassium, I have 26.6 grams, okay? Potassium has a molecular weight of 39.098 grams per mole, according to our periodic table. So we're going to say this, we're going to bring grams of potassium down to the right, and we want to convert it into moles. So 1 mole is equal to 39.098. So when you type that into your calculator, you should be getting, I'm going to go to, once again, just 2 decimal places just to keep it a little easy on us, 0.68 moles of potassium, okay? All right. For the next one, we have 35.4% chromium, so 35.4 grams of this chromium. We know that chromium's molecular mass is 51.996. So we're going to divide by that, 1 mole, okay? And we should be getting 0.68 moles of chromium. So as you can see, got the same number here. Finally, we have 38.1% or grams of oxygen. So we're going to divide it by its molar mass, 15.999, to get 2.38 moles. So we've now done grams to moles. We're going to divide by the smallest. So the smallest number in this list of 3 is 0.68. So we're going to divide everything by 0.68. Okay. So obviously our potassium is going to come out to 1. Chromium will come out to 1. Oxygen, however, will come out to be 3.5. So this is where we would say, okay, well those are all your subscripts. However, since we have this 3.5, I'm going to take all of these numbers and I'm going to multiply them all by 2 in order to get a whole number for that last one. So we now have 227. So my answer here is actually going to be K, oops. There you go. We're going to have K2 Cr2O7, okay? And what this actually is this is dichromate, and this is potassium, so it's potassium dichromate, which is an actual thing. So cool. So we got there. Now we want to know what is the actual molecular formula of that, though, okay? So molecular formula, we're going to use that molecular formula mass that they give us, which is 200, let me write that a little bit nicer, 294.2 I'm going to divide it by this mass. So adding up all of these, okay, if you look in there, you would get 294.181. So I'm going to divide it by 294.181. Hopefully you're not going to type that in. Because looking here, what is that about? It's about 1, right? So we're going to say molecular formula is equal to empirical formula for this problem. So the true formula is potassium dichromate. Okay? So that's your empirical formula and molecular formula. Next, we have stoichiometry problems. So what I'd like to do is do a quick review over what I usually teach, which is the mole bridge, mole world, all that stuff. Okay? All right, so stoichiometry world. We have, in the center of stoichiometry world, we have mole town. Okay? Mole town is something that you have to cross no matter what, or go through no matter what, if you're converting between different things. Like we saw in the chart a couple problems ago, number 16, right? So we had conversions between moles and number of particles. So we call this particle city. Okay, or chemistry word city is another way to say it. Okay, so that's anything like formula units, atoms, molecules, any of that, okay? And in order to get to this particle city, you have to take the Avogadro express. So you have to use that Avogadro's number in order to get those conversions. We also have Gramland. Okay? And so to get to Gramland, you have to use your molar mass. I think we said carriage last year. So you have to use your molar mass, though, to convert between moles and grams, right? And then finally, one that we're not going to use, I don't think in the summer assignment, but just be aware of it for the first couple weeks, is Volumeville, all right? So Volumeville we deal with when we are talking about gases, right? And so for Volumeville, you have to ride the B 22.4, okay, which is add STP, all gases, 1 mole of any gas is 22.4 liters, okay? So, so you do have this whole thing. One special thing is that when you're usually doing stoichiometry, we're usually only dealing with either Gramland or we're dealing with Volumeville, okay? But more importantly, the basic one is usually between mole town and Gramland, okay? But something that's important is that if we start in Gramland, we use our molar mass to travel to mole town. The minute you're in mole town, you have to do something. You always have to go see the mole bridge, all right? So no matter what, if you are traveling to mole town and you are changing characters somewhere in your problem that's given to you, you have to cross that mole bridge. And that's where you do a mole ratio, okay? Mole ratios use your coefficients, okay? The big numbers in front of all of your little chemical formulas in your problem. Okay, once you cross that mole bridge, now you're safe to come right back, okay? But that's the basic idea. So I'll leave this off in the corner over here so you can kind of refer to it if it helps. Some of y'all really relied on that last year. But looking at our problem, it says complete the stoichiometry problem. So determine the amount of iodine produced when 145 grams of potassium iodide. So I always like to start writing in things as I'm reading them. So I'm just going to write in, did it again, 145 grams of potassium iodide react with excess copper chloride. So whenever I see the word excess, I like to go over here and I go X, because that's not going to be the one that determines how much is done. Number 21 is a limiting reactant problem. We'll go over that when we get there. So we're going to start with our 145 grams of potassium iodide. I create my mole, or my railroad tracks. I'm going to bring words down and to the right. Okay, so I'm in gram land right now, right? I need to get to mole town, so I'm going to use my molar mass. So I know that 1 mole of potassium iodide has a molar mass of 166.002. And I got this from the periodic table, right? So this is from periodic table. All right, now I'm going to take words down to the right, because we're still sitting here trying to cancel things out. So now I've just done that. Okay. And what we have is we know that we need to, in mole town, cross that mole bridge. So we're going to cross the mole bridge. So we have a mole to mole ratio. We're going to make it be iodine, which is this I2. He's diatomic. Okay. And we're going to look for our coefficients. This is your mole bridge. So looking for our coefficients, we have a 4 here and we have a 1 here. So it's a 4-to-1 ratio. And I'm going to continue on because they want to know the amount produced. So let's go ahead and just take it to grams. You could stop there if they wanted moles. But I'm going to take this down. I'm going to say moles of iodine into grams of iodine. And so when I do that, I'm going to have 1 mole of iodine is equal to 253.81 grams of iodine. Okay? When we have that, what we're going to do is we're going to go ahead and multiply. I would do everything on the top. Multiply everything, push equal on your calculator, and then you do division on the bottom. So some people like to multiply everything on the bottom and then divide 2 big numbers. What I like to do is I get everything on the top, and so I'll have this number, and then I will push divide, and I would say 166.002, and then I would push divide, and I would say 4, and I could say divide 1. And then you push equals. When you push this division over and over and over in your calculator, it actually takes into account all those guys underneath. And I think this is the best way to do it without getting any rounding errors. So in conclusion, what you would get is you would get 55.42 grams of iodine produced. Okay, and that's your answer for that one. All right, our final question for this video is going to be finding your limiting reactant and calculating. You want to determine the moles of CO2 and H2O. So please note this is moles. We don't have to go all the way to grams, which is nice. Formed when 2 moles of ethane are reacted with 10 moles of oxygen. So when you are doing limiting reactant problems, okay, remember your limiting reactant, the way we probably taught you is with s'mores, right? So you know that you always have 2 graham crackers, right? We always have 1 marshmallow, and I believe I used like 3 pieces of chocolate. My favorite s'more is the one that doesn't have the marshmallow or the graham cracker in it, if you get that. All right, but so let's just say this was your recipe for that. Then if I tell you that you have 26 graham crackers, you have 14 marshmallows, and you have 18 chocolates, right? You want to determine how many can you make of each. So if you have 26 graham crackers, you're seeing that you can divide it by 2, and you would have 13 s'mores possible. 14 marshmallows gives you 14 s'mores possible, and 18 chocolates would give you 6 s'mores. So obviously our chocolate is the one that's going to limit us. We can't make 13 if we don't have the ingredients. We can't make 14 if we don't have the ingredients. So your limiting reactant is the one that stops the reaction because it runs out first. Okay? All right. So in chemistry terms, you're usually given some sort of a balanced equation, and we're asking you to figure out which one is limiting, right? So the best way to do that, that most of you guys did, was you take the amount that you have that's given to you, and you figure out, you only have to test one of them to figure out which one runs out first, okay? And so we could say 2 moles of ethane, right? So 2 moles C2H6, okay? And if I want to know how many moles of carbon dioxide were made, I would say mole of ethane to mole of carbon dioxide, okay? So looking here, this is our mole to mole, so this is where we take our coefficients. It's a 2 to 4 ratio. So looking here, you can kind of do this mentally. You have this, you can get 4 moles out of ethane. When we look at oxygen, okay, we're going to start with 10 moles of oxygen, okay? We're going to go mole of oxygen to mole of carbon dioxide. We have a 7 to 4 ratio, okay? So looking here, you would figure out that this is about, what, 40 divided by 7, so it's between 5 and 6-ish, right? So 5 to 6. So which one of these is in excess? That would be oxygen. So we're going to chop out oxygen, and the only one that matters is going to be ethane, because this is the one that's going to run out first. So this is going to determine how much of your products are made. So we've already figured out 4 moles of CO2. Let's go ahead and go back, and we can say now 2 moles of ethane, and now we want to figure out the moles of water. So we know it's a 2 mole ethane. Please remember, by the way, this 2 and this 2 are not the same thing. This was given to us in the problem. It's really actually 2.00, right? And then when we get here, this is our actual mole bridge, right? So we have a 2 to 6 ratio for the water, okay? So 2 times 6 divided by 2 is going to give me 6 moles of H2O. So really, this is a super simple problem. You will obviously have a lot more difficult than this, but this was just to remind you how to find your limiting reactant. Now, on that note, I'm going to also show you the shortcut that I had taught last year. That shortcut is you look at what you have, right? So if I have 2.00 moles of ethane, okay, and 10.0 moles of oxygen. H6, there you go. All right, you're going to take this, and you're going to divide it by your coefficients. So 2 divided by 2, 10 divided by 7. You get 1, you get about 1.5-ish, okay? So looking at that, you know, once again, oxygen is in excess. This guy is the one that's limiting. Now, the tricky part about this is that make sure you are in moles. If I would have changed this and said you had 5 grams of ethane and 18 grams of oxygen, you would first have to convert these into moles before you can use this shortcut. However, this shortcut is really going to help you when you get to multiple choice questions. You don't have to work through all of these, okay? It's really a good way. So make sure you always divide it by its molar mass if it is given to you in grams, and then you continue on to this step and divide by its coefficients, okay? And that's the shortcut on finding your limiting reactant. So hopefully this helped you. With through 21, I think we just have a few left. So in the next video, you can expect that. See you then.